Hi everyone and welcome back. In the last video, we built a complete neural network from scratch entirely using maths and diagrams. We went step by step through forward propagation, loss function, and back propagation using a real example. So here's a quick recap. We had 3 input samples, each with 2 features. These passed through a hidden layer with 3 neurons, followed by a single output neuron. For activation functions, we used ReLU activation function in the hidden layer and Sigmoid in the output layer. We also covered the binary cross-entropy loss in the last video and also calculated the gradients and saw how to update weights manually. If you haven't watched that video yet, I highly recommend doing that first. This one builds directly onto it. In this video, I'll implement everything in Python using NumPy. The same network we built by hand, I have already written the code, and I will walk you through it line by line. Feel free to follow along in a Jupyter Notebook. It's a great tool to run Python code interactively, visualize outputs, and experiment as you go. We start by importing the NumPy library and give it as name as np. So import NumPy as np. NumPy helps us handle vectors, matrices, and mathematical operations efficiently. We define the input matrix x just like before in our example. So here you can see we had defined wx is equals to this matrix. We are also initializing the same in here Python code. So each row represents a sample and each sample has 2 features. Now we define the true label y, which is equal to 1, 0, 1, same as in our previous example. And then here is weight initialization. We initialize weights manually. So w1 equals np.array. First neuron weights 0.4 minus 0.6, same as this one. Then second row and the third row. b1 is equal to, I have initializing same as before, 0.2 minus 0.1 and 0.5. Later on, when you scale up your network, you can initialize weights randomly, which is usually done by this line of code. W equals np.random.randn. Number of input dimensions, in our example there were 2, and then output dimensions will be same as the number of neurons. So if I have 100 neurons here, I will be initializing it with 100 neurons and then multiplying it by 0.01. Then the activation functions, we define the ReLU activation function and the Sigmoid activation function. We also define their derivatives, which are needed for back propagation. Don't worry if these derivatives seem unfamiliar. I'll create a separate video to walk you through the math behind them. So for the forward propagation, we compute the dot product of inputs and weights and add a bias and apply the activation function. So we had seen this formula, z equals x dot, the dot product of x times the transpose of weight matrix plus the transpose of a bias matrix. I'm doing the same here. The output from these neurons will be used as an input in this output neuron. So this is what I'm doing here. Instead of writing x, I'm using a1 dot product with the w2 matrix and adding the bias term and applying the sigmoid activation function later on. So let me run the code here again. I'll press the shift and then click enter. It will run my code, and as you can see here, it calculated the predictions. These will be same as we had calculated in our previous video. So the z1 equals let me check. No, I have not added the print statement here. So let me write z1 and print a1 as well. So as you can see here, the sample one has minus 0.8, same as this one, 2.5 and 0.4, which matches from our previous example. And for the activation function, you can see that it is 0, 2.5 and 0.4, same as this one, right? So these steps mirror what we did manually. We did the matrix operations, activations, and then predictions. For the prediction, I will scroll below, and here you can see what our model had predicted. So these are same as our model is predicting. So we already did that in our previous example. Then finally we will find the binary cross entropy loss. It is defined by this formula. We had discussed this formula in our previous video. So loss equals to this formula. I'm just translating it in my code here. And np.clip, we are using this function to avoid taking the log of 0. As you know, like as you can see here, we are using log of y prediction. If the y prediction is 0, then it may cause errors. Therefore, I'm using np.clip function here. Then I'm defining the binary cross entropy derivative. As I already suggested, I will make a detailed video on derivatives and the chain rule and the backpropagation. So for now you can write it as it is. And then finally we set a learning rate and run a loop for multiple iterations to perform forward propagation, calculate loss, perform backpropagation, and update the weights. So here you can see that learning rate is 0.1. You can initialize it as 0.01 as well. And then I'm running this loop. Let's say I'll run it for 10 times. Then after running the forward propagation, defining the loss, calculating the loss, and running the backward propagation, I am updating the weights in this code. So this was already defined. Loss equals to, I'm calling this binary cross entropy function that we initialized here. And then the backward propagation, I'm just finding the partial derivatives, and finally I'm updating the W2, B2, W1 and B1. We had already discussed literally everything that I'm telling you here in our previous video, so I'll encourage you to watch that one as well. We updated the weights, and then let me print the iteration and the loss. So I will first run this code and then this code. So in our first iteration, you can see that the loss function is loss is equal to 1.3536, which is nearly equal to this one. So we had already found the loss function for first iteration, and then slowly and gradually as the weights, we update the weights, our loss will be decreased. So in order to make predictions, let me run this code for, let's say, 1000 times. So instead of printing the this line 1000 times, let me add the condition here. So if epoch modulus 100 equals 0, then print this code. So if I run this again, as you can see here, with each 100 iterations, the loss is decreasing. So as you can see here, the loss is decreasing after each iterations. And finally I am doing the final predictions. So this is the let me run this code first, and then let's compare with the true labels. So our true labels 1, 0 and 1. So it predicted 0.99. so sample 1 was true, and the predictions for sample 1, it predicted 0.997, which is very near, right? And for the sample 2, it was 0, and then our model predicted 0.001, and for sample 3 it was 1, and our model predicted 0.99. So if I run this for 1000 times again, our weights will be updated, and then on those updated weights, let me predict again. Okay, so it showed me these predictions, but in order to see these numbers without scientific notation, let me just add one more line here. So set print options suppress equals true. Now this will show us numbers in non-scientific numbers. So if I run this one, as you can see here, this one is equal to 1 and this one is equal to 0, and then finally this already outputs are predicted as 1. So if you run this enough time, like I would say that 1000 times is literally a large number, and then we already saw that it was predicting nearly same as our y labels. And as you can see, the model performs well. Even this simple network can learn. We have successfully translated our handwritten and hand-drawn neural network into real Python code. No TensorFlow and no PyTorch, just NumPy. We controlled everything: weights, matrices, activations, loss, and gradient updates. In the next video, we will apply the same structure to recognize handwritten digits using a basic image dataset. We will build a tiny image classifier completely from scratch. If you found this video helpful, like, comment, and subscribe for the next lesson.